Hello everybody. So today we're going to talk about several special types of graphs. So some special graphs. So the first example is the complete graph. I think I already introduced this the complete graphs last week, but let me talk a little bit about them once again. So in particular, there is a notation. So Kn denotes a complete graph on n vertices. So let's see some examples. So K1 is kind of silly. It's just one vertex, so there are no edges. So K2 will look like that. That's just one edge connecting two vertices. Then K3 is a triangle. So three vertices, all of them connected. K4 is a square with both diagonals. One can also draw K4 a bit differently. So, for example, like that. And maybe one more example. So K5, we have 5 vertices, and all of them are connected. So it's going to look like that. 5 gone, and all the 5 diagonals in the 5 gone. So that's K5. Now, kind of the opposite example is the empty graph. So it's a graph with no edges. So that's kind of a very silly example. That's E1, empty with graph on one vertex. That's just E2. So we just have vertices and we don't have any edges. E3, E4, E5. So another type of graphs, or let me separate this so that it's clear what's going on. Maybe the same here. So another kind of type of graphs, or rather an operation on graphs, is the complement. So if you have a graph, then what one can do, one can take its complement. So the formal definition, so this is the notation, we put a bar for the complement, and the definition is as follows. The complement has the same vertex set V, but the edge set is kind of the opposite. We have an edge UV if and only if UV is not an edge in the original graph. So for example, so the complement of the complete graph is En, clearly, right? So if you had all the edges, then the complement won't have any edges. And another observation is that if you take the complement of the complement, you recover the graph itself. So you take, because first time you take all the edges that were not in the graph, and then as you repeat this procedure, you recover the graph you started from. So let's consider a concrete example over here. So this is the graph G. Now I want to draw the complement. So the way I will do it, I will take a copy of this one. Now what I will do, I will draw the edges that are not there in red. So okay, let's start from this vertex. It's connected. Oops, didn't want to do that. It's not connected to this, but it's connected to everything else, right? So there are 6 vertices. So okay, we're missing one edge here. So here we are missing what? 3 edges. 1, 2, 3. Now here we are still missing 2 edges. 1 and 2. Here we are still missing 1 edge, and I think that's it. So here we have all the 5 edges, and here we also have all 5 edges. And now what I will do, I will just remove the old edges. from this graph. So all the orange edges. So I remove this, 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 this. So that is now the complement. So note that maybe I should emphasize that this is a vertex over here. So that's the complement, G bar. So note that, of course, if I repeat this procedure, I will recover the graph I started from. Now another type of graphs. So this is kind of a more wide type of graphs than empty graphs or complete graphs. So these graphs are called regular graphs. And the definition is as follows. A graph is called regular if all the edges have the same, what is going on? Have the same degree. So all the edges have the same degree. So moreover, a graph is called k-regular or regular of degree k if all edges have degree k, precisely. So if I want to emphasize the degree, then you can say k-regular. So some examples. So first of all, of course, Kn, so the complete graph on n vertices, is regular of degree n-1 or n-1 regular. So of course, every edge in the complete graph is connected to every other edges, and there are n-1 other edges, so it is regular of degree n-1. So note that vice versa, if you have an n-1 regular graph of order n, it will have to be complete, because if an edge has degree n-1, that means that it is connected to every other edge, and that has to be true for all the all the vertices. If a vertex has degree n-1, then it is connected to all other vertices, and if this is true for every vertex, that means that we have a complete graph. Another example, En, so the empty graph is of course zero regular, so every vertex has degree 0, so that was kind of easy, clear. And one more observation is that if you have a regular k-regular graph, G, then its complement is going to be n minus k regular, where n is the order of the graph, so it's the number of vertices in our graph. So of course this is also kind of true, kind of clear here, of course. And here are some concrete examples. So this is this graph is what? It's 4 regular on the left, and the graph on the right is what? It's 3 regular. You can check that all the vertices have the same degree in each of the pictures. Now, the next type of graphs that I want to introduce is called cycles. So it's just cycles, Cn. So Cn is the cycle on n vertices. Or cycle of length n. So since it is a cycle, number of vertices is equal to number of edges. So for example, well, yeah, n should be greater or equal than 3, otherwise it's not gonna really make sense. Well, I mean, for n equal to 2, you might consider a multigraph with 2 edges and call it a cycle of length 2. But since we're talking strictly about graphs, we need at least 3 vertices to form a cycle. So here is the C3, so cycle of length 3. Then foregone is C4, and so on. You might draw it in some fancy way as well. So maybe something like that. What did I want to draw? Like that. So that's a C5. And so on. So now we also have paths, so it's kind of just when all of them, all the vertices are just in one line. So path, so Pn is the path on n vertices. Or of length n minus 1. Remember that the length of a path is a number of edges there. So this is let me check real quick. What I wanted. Yes, so this is P2, right? And P3 will look like that. And again, you can draw it in some fancy way if you want. So that's a P4. And so on. Now, the next thing I want to talk about is a subgraphs. So if you have a graph, then we can talk about subgraphs inside that graph. So a graph G prime is called a subgraph of a graph G if, well, basically we just have two conditions, that the set of vertices is a subset in V in the set of vertices, and the set of edges in G prime is a subset in the set of edges of G. So here I had a typo. This is set of edges in G. So, well, here is an example. So I have a graph G, and if I want to consider a subgraph, well, what do? Let me copy it and just remove some of the stuff from it. So let's say I want to remove this vertex and these two edges. So that's a subgraph. Now there is a special type of subgraphs called induced subgraphs. So what is that? That means that so that means that basically we are only allowed to remove vertices, and with each vertex we of course remove every edge going from every edge that has this vertex as an end vertex. In other words, we can do it in the following way. We can say that let's say that we have a set S of vertices, so a subset in the set of vertices, and then we say that the subgraph is induced by S and denoted well in this S in this parenthesis. If the following holds, so the set of vertices of our subgraph is S, and the set of edges consists of all the edges of G such that both end vertices belong to S. So basically the set of edges consists of all edges UV such that both U and V are in S. So a remark is that actually we already saw this construction in a different kind of flavor. So basically the graph induced by S is nothing else but the graph with all the vertices except for the vertices in S removed. So we remove the complement. We remove all the vertices except, so this is the this is a set minus basically, right? Set minus. So basically I take the vertex set and I remove S from it. So I take all the rest of the vertices, and then I need to remove them from my graph G, and that's going to be the induced subgraph. So here are some examples. Here is an example. So let's say we have this graph here, G, and let's say that we have this set S consisting of vertices A, F, H, D, and J. So now what's going to be the graph induced by this subset S? So basically what I need to do, I need to remove all the all the vertices that are not in this subset. So I do keep A, but I remove B, and I remove together with B, I remove all the edges from B. So I remove like that. Then A, B, C is also removed. C is also A, B, C, D. We keep D. E, when you remove E, A, B, C, D, E. F, we keep. G, we remove G. H, we keep. I, we remove. J, we keep, and F, we keep. So that's the subgraph. So just to check, we're supposed to have 5 vertices, and indeed we have 5 vertices here. So that's an induced subgraph. Well, I left some. Yeah. So yes. So that's all I wanted to say in this video. Thank you very much, and stay tuned for the next video as well.